So in this video, we're going to talk about some elementary concepts of electricity, and then we're going to talk about some of the units that we use to represent electricity. So to start with, we know that every atom is made up of a nucleus, typically with protons and neutrons, and then we've got a bunch of electrons going around, right? So this is fairly typical. We understand this. Now, when we look at things on a level of materials, so let's say we've got a long cylinder of two different materials. Right? Let's do this material, and then let's do one in that concept. So, to start with, we know that every atom is made up of a nucleus, typically with protons and neutrons, and then we've got a bunch of electrons going around, right? So this is fairly typical. We understand this. Now, when we look at things on a level of materials, so let's say we've got a long cylinder of two different materials. Right? Let's do this material, and then let's do one in that. So different materials will have their electrons arranged a little bit differently. Some materials, and typically we think of metals, some materials have their nuclei arranged fairly closely together, and then they have their electrons kind of moving around in a little bit of a, you could say like a little bit of a soup. And the electrons are very delocalized, right? And so this is classic in metals, and these are known as metallic bonds in metals, right? The nuclei themselves are kind of more or less stationary, and the electrons are kind of free to move around between the materials. And so what happens is that the electrons can move around fairly easily, and so that means that electrons can move, for example, from this point to this point very easily. And so that means that this material is a conductor, right? Each nucleus doesn't hold its electrons very tightly, but the material as a whole allows electrons to flow, right? Whereas if we contrast that with a material like this, we could say, for example, this might be wood or it might be rubber, right? And what would happen with these materials is these materials are a little different, right? These materials typically will hold their electrons in a different arrangement. So these materials will hold their electrons, each individual atom or each individual nucleus will hold its electrons fairly tightly. They might share electrons, right? They might share electrons with one another. And so there are going to be a lot more nuclei than that, obviously, but they might share electrons, but at the end of the day, this guy is not going to give up his electron and allow it to go there, so that's not going to happen, right? And so this is what we would call an insulator. And the classic example of conductors are metals, and the classic example of insulators, I would say, is wood or rubber. There are some other types of examples that we use industrially, but those are two examples that I think we should be aware of. Conductors are metals, for example, copper or gold. Those are very great conductors. Most metals are very great conductors. Insulators are examples are wood and rubber. So now we know that charge, which is we understand in the form of electrons. Electrons can flow. Electrons can move around. Electrons can be moved from one atom to another, right? And it turns out that we represent this concept as charge. So each electron has one negative charge. And when we talk on a macro level, on a level that we can see with our eyes, we talk not in terms of individual electrons. We talk in terms of coulombs, right? So coulomb is the unit that we use for charge. Coulomb. Right, we talk in terms of coulombs. And 1 coulomb is represented as lowercase c, is equal to 6.24 times 10 to the 18th electrons. Now, this number you don't need to memorize. This number, the MCAT will give you this number if it ever needs you to use it. But do be aware of this number. Right? 6.24 times 10 to the 18 electrons flowing is 1 coulomb. So what that means is that if we've got, for example, if we got this, say this is box X and this is box, let's make it a different color. Let's make box Y, right? And these are neutral. These have no charge to start with. And then what happens is we transfer 1 coulomb of electrons from here to there, right? And so what happens? Well, what's going to happen is there's a concept called conservation of charge. We didn't create charge out of nowhere. We moved the charge from one atom to the other, or from one object to the other. So in this case, the charge on these objects, the charge on object X is going to be plus 1 coulomb. And the charge on object Y is going to be minus 1 coulomb. Right? We know that because we moved 1 coulomb of electrons, or 6.24 times 10 to the minus 18. Well, technically we moved negative 1 coulomb. That's a little confusing. But a coulomb is a unit of charge. So this is plus 1 coulomb, this is minus 1 coulomb. And this has this one has this many extra electrons, and this one is missing this many electrons, right? So electrons are always the things that move. We'll never see protons moving in this context. So now that we understand conductors, insulators, and we understand coulombs, let's talk a bit about the flow of charge. Right? So now we understand that charge can move from one object to the other. But there are situations in which we can make charges move, right? And so a classic example is a battery. Let me draw a battery. And essentially what a battery is and we'll talk a lot more about it in electrochemistry, but a battery is essentially a chemical reaction that on one side generates a positive charge, and on one side generates negative charge, and on the other side it generates we could say a desire or a potential for positive charge. And so what happens is typically these would be separated by some sort of a barrier. And so what happens is the electrons on this side really, really want to go to this side, but they can't. They're blocked. And so what happens is we create a circuit. Right? And so we create a circuit. And actually, before we draw the circuit, we put something for the electrons to do, right? So if we were to just draw a wire, the electrons would start zooming very fast, and they would exhaust the battery would be dead very quickly, and it wouldn't really do anything for us, and the circuit would get very hot, the battery would get very hot, the wire would get very hot, and nothing would really happen. So instead what we can do is we can make them power a light bulb, or anything really. Let's say we can make them power a light bulb. And so now the electrons will power that light bulb, and on their way down the circuit, right? So this is a different color for that. So the electrons, as they're moving down the circuit, they'll power this light bulb, right? And then they'll move to the positive terminal. And so this is the way that we can conceptualize electricity. So it turns out that there are a couple of concepts that we should be aware of as far as the movement of electrons also. So the first thing we should be aware of is the concept of voltage. Let's write it here. Voltage. Voltage is the desire, essentially, of the electrons to move from this point to this point. And so we can think of it as really potential, electric potential. And so, so for example, if we add a lot more electrons on this side than we do on this side, then the voltage is going to be higher, right? And if we got fewer electrons on one side than on the other, then the voltage is going to be lower. So voltage is one concept that we should be aware of. It's the essentially the desire or the potential for electrons to move from one point to the other, right? So if I ever create, so for example, let's go back to this object over here, this drawing that we drew over here, right? Well, we moved electrons from one point to the other, right? Well, now what happened is we created an electric potential. Because this side is positively charged and this side is negatively charged, the electrons on this side want to go back to this side. They always, positives attract negatives attract positives, and so the objects on the negative side want to go to the positive side. So how are they going to do that? Well, at the moment they can't, but if we were to connect them, then that electric potential, that voltage between them, would then be converted into energy. The electrons would move from this side back to this side. And so that's one concept to be aware of, is voltage. Then the other concept to be aware of is the concept of current. So we said that if we were to connect them, the electrons would flow, right? And it turns out that the flow of electrons moving from one point to another, is also known as current, right? So a current is the flow of electrons from one point to the other, and the units that we use for current are amps. So current is represented typically with a variable I, and the units for current we use are amperes or amps. And the equation that we should understand for current is measured in coulombs per second, right? That is to say, the amount of charge that moves from one point to the other each second. And so current is measured in coulombs per second. 1 amp is equal to 1 coulomb per second. And so current moving from one point to the other is measured in coulombs per second. That is current. Voltage, by the way, is measured in volts, and typically represented with a lowercase v. Typically, so for example, this battery might have so you've probably heard of a 9-volt battery, for example, 9-volt battery, right? And so this is how we would draw this is how we would understand voltage. And so those are the concepts of voltage, current, and the coulomb. All right, so how do we solve this question? A particular battery can provide 3 amps of current for 2 hours. How much charge can the battery provide? So we talked about how amps, or current, is essentially charge per second. So amp equals coulombs per second. Right? Okay, so what we want to do is we want to 3 amps. We know we have 3 amps, and we know it can provide that for 2 hours. So the question is, how do we convert 2 hours into seconds? So 2 hours equals, well, we know that there are 60 seconds equals 1 minute. And we know that there are 60 minutes in 1 hour. So when we multiply these, we end up with 3,600 seconds equals 1 hour. And so what that means is that there are 3,600 seconds in an hour. We have 2 hours, and converting that into hours, 3,600 seconds times 2, it's 7,200 seconds. So we are generating a current for 7,200 seconds, right? So now let's plug that into this equation. So we've got 3 amps, and we've got coulombs over 7,200 seconds. 7,200 times 3 is going to be roughly 21 something, right? 3 times 7 is 21, and then we can estimate that, the rest of that 21,000. And so based on the option choices, we look and we see that this one is the best option, 21,600. And indeed, 3 times 7,200 equals 21,600. And that's how we solve a problem like this. It relies on us realizing that current is charge per second. Current is the amount of charge per second, and then just converting hours into seconds.